In the last lecture, we have finished the concept of heat and temperature. Now we are starting the next topic, factors on which amount of heat absorbed depends. What does it mean? You can find this topic in page 262 of Selena publication. Now, it is said, it is very common sense that if I have 1 kg of iron and 50 kgs of iron, if I try to heat this thing and increase its temperature by 5 degrees centigrade and its temperature by the same 5 degrees centigrade, will these both objects take equal amount of heat? So 1 kg iron and 50 kg iron, for increasing the same amount of temperature, the answer is no. They will not take same amount of heat because this iron is 50 kg and this iron is 1 kg. So this one is supposed to take more amount of heat than this one. So with increase in mass, we require more amount of heat. Means in case of 1 kg, as we are taking 50 kg, so we will require more heat in this case. And if I take another iron piece which is of more large, 100 kg, it will require more heat for the same temperature increase. So from here we can possibly conclude that the amount of heat required, that is Q. What is Q? The amount of heat required. This value is directly proportional to mass of the system. Means more the mass, more amount of heat is required. I will mark this equation as equation number 1. It's basically common sense. If your object is having more mass, it will take more amount of heat. Clear? Now, the next thing is that this is the first thing we have understood, the mass dependence. The next thing is that value of temperature. Means how much temperature we are going to increase. That means you take a system 2 liters of water. You first decide to increase the temperature by 5 degrees centigrade, in the next case 25 degrees centigrade, in the next case 50 degrees centigrade. For increasing 5 degrees centigrade, you need some amount of heat. For 25, the amount of heat required is more than 5. And in case of increasing by 50 degrees centigrade, we will require much more amount of heat. It's common sense that if I want to increase the temperature by a greater value, I will require a greater amount of heat. So we can conclude the second theory that the amount of heat required, again Q, is proportional to how much temperature you want to increase. In short, delta T, where delta T represents the increase in temperature. The delta T represents the increase in temperature. So the heat required is directly proportional to temperature increase. So we get two formulas out of here. Factors on which required heat depends. The first factor is mass. That's a directly proportional relation. The second factor is also a directly proportional relation with change in temperature. In mathematical form, Q proportionals to delta T, where delta represents the change, T the temperature. Now if I compile this equation 1 and equation 2, all of you know, if two proportional relations are compiled, 1 and 2 gives us Q is proportional to M delta T. Q proportional to M, Q proportional to delta T. Together, Q proportional to M delta T. Clear? Now is this an equation? I think all of you know the answer. The answer is no. This is not an equation, because an equation will always contain an equals to symbol. But is there an equal symbol? The answer is no. That is a proportional relation. So what is required to convert an equation to a proportional relation? We multiply it by a constant. In our case, the constant is C. If I multiply the right hand side by the constant C, I will get the equation Q equals to mc delta T, and that is the equation of heat required. That is the equation of heat required, where Q is the amount of heat, M represents the amount of mass required, delta T represents the change in temperature, and C is the constant. C is the constant. Fine. This is the equation, the final equation to calculate the amount of heat required to increase the temperature by a value delta T for a mass of M, where C is the constant. Now the question appears that what is this C in this equation? What is this C in this equation? This C is basically known as, it's a physical quantity which is called, specific heat capacity. It will be more clear if I break its equation. Now Q equals to mc delta T, we just got here. So what is C? Q by M into delta T. That's the equation for C. This is the equation for C, which I called specific heat capacity. So what is that? Now C is basically amount, Q is amount of heat required by the mass, which stands for M, into change in temperature, that is delta T. So basically specific heat shows the amount of heat required per unit mass per unit temperature. That means if I want to increase the temperature by a unit value, that is 1 degree, of a mass of 1 gram substance or unit mass, the amount of heat required is C. Example, if I want to increase the temperature of 1 kg object by 1 degree centigrade, if I need 15 joule of heat, then the specific heat of that substance is 15. Clear? So specific heat capacity stands for amount of heat required for a substance of unit mass for increasing its temperature by unit value, that is like 1 degree centigrade or 1 Kelvin, whatever you prefer, same thing. Clear? Now what is the specific heat capacity doing in this equation? Let's discuss the thing easily. So the specific heat basically, the specific heat capacity, the full name, basically depends on the material. Depends on the material. Just think, we got the equation Q equals to mc delta T. Now I take 10 kg of iron and 10 kg of plastic. So in both cases mass are same, both are 10 kilograms. Both of their temperature must be increased by 10 degree centigrade. Means I will heat the iron by 10 degree centigrade and I will also heat the plastic by 10 degree centigrade. That means delta T is also same for this case. See, in our equation M and delta T both are same, but will they take equal amount of heat? The answer is no. Why not? Because iron and plastic are different materials, so they will take different amount of heat to increase their temperature by the same amount, and that thing on which this material quality depends, on which depends how much heat we will take, that thing are different for each and every material, and that thing is C, the specific heat capacity. So it basically represents that which material will take how much amount of heat to increase its value by same amount of temperature. Clear? So I hope this much is clear to all of you, the concept of specific heat capacity. In your book you will find out the list of things where it is given a chart for each and every materials. We will come to that topic later. One more thing is that we have to discuss here about heat capacity. I am making it clear again. The previous topic was specific heat capacity. The term specific was an extra. Here we are discussing about heat capacity. No term like specific. So basically they are very same things, differs by a single thing. Heat capacity is the heat required by the system to increase its temperature by 1 degree centigrade. Clear? No concept of unit mass, no concept of 1 gram or 1 kg. So basically what is heat capacity? It is heat required per unit temperature increase. No mass term. And what was specific heat? The specific heat required is the amount of heat required per unit mass per degree centigrade. Clear? So this specific heat capacity is usually represented by a small c, whereas the heat capacity is represented by a capital C. So we can see the very easy relation and the very easy differences. Specific heat capacity, and in this side we get heat capacity. Clear? Specific heat capacity is small c Q by m into delta T. Heat capacity is capital C representation and Q by delta T. Clear? These are the difference in the equations. Clear? It depends per unit mass. There is no mass dependence. It's just temperature dependence. So specific heat capacity and heat capacity are two very different things, and they can be related with each other. We will show the relations. The references are written in your book, the portion 11.7, end of the page 264. So now I'm coming to the relation in between them. How can I relate the heat capacity and specific heat capacity? The relation in between. Clear? Now specific heat capacity, the small c is Q by m into delta T, and he is a specific one. Specific heat capacity, I'm repeating again and again, and this is just heat capacity, that is capital C, Q by delta T. Now the specific heat C equals to Q by m delta T. Can I write this as 1 by m into Q by delta T? Yes. Yes. Q by m into delta T. I just took 1 by m common, Q by delta T inside the bracket. Now Q by delta T is specific heat capacity. Q by delta T is already known to us as heat capacity. So instead of Q by delta T, I can write the capital C into 1 by m, the 1 by m, and Q by delta T is capital C. So this is the equation final form, that specific heat capacity is equals to C, that is heat capacity per unit mass. I can also write like this. Theoretically, specific heat capacity equals to heat capacity per unit mass. Clear? That's the mathematical form, and that's the theoretical representation of the relations. Clear? So that's our topic with specific heat capacity and heat capacity and their differences, and how are they related with each other. So now the final thing when we study any object, very important thing is to learn their units, because any physical quantity is strictly dependent on their units. So we learned two topics. One is specific heat capacity, and the second thing we learned here in this video is heat capacity, the capital C and here the small c. Very easy. The units can be determined from their formulas. You don't need to remember them. These are the respective formulas of those systems. Now I just run in the units. So it is specific heat capacity is Q by m delta T, where Q is heat, m is mass, and delta T very easily temperature. If I am looking for SI units, what is the unit of heat? Joule. The joule goes for heat. By mass is in kg, and of course delta T, temperature in Kelvin. So what I got? Joule per kg Kelvin, that is J per kg into K. Kg for kilograms and K for the Kelvin. and J for joule. This is the SI unit of specific heat capacity. Clear? Here the things are a little different, not much. Heat capacity is basically Q by delta T. Q is heat, so joule, and delta T, that stands for temperature here. So joule short form J, and temperature in Kelvin, that is temperature in Kelvin. So joule per Kelvin, joule per Kelvin, that is the case for heat capacity. So we can see here again they are differed by a quantity of mass, as specific heat quantity is having m in the formula, so the kg portions appear, and in heat capacity no mass dependence, so no kg portions in the formula. That's all we have to learn from here. Now any numericals examples can be done. Any kind of heat is given, you can calculate out its specific heat capacity. So I hope that is helpful. Thank you.